Let's look at one more example for this video. Next up, I would like to find the area bounded by f of x equals 2x squared and g of x equals 4 minus 2x on the interval negative 2 is less than or equal to x is less than or equal to 1. So here the first thing I'm going to do is I'm going to graph this interval, graph these two functions. So we have 2x squared. I know that's a parabola centered at the origin that's opening upward. Oops, let's make that a little bit better. And then g of x equals 4 minus 2x. I'm not going to get too specific here, but I know that the y-intercept is positive, so I'm going to go up 1, 2, 3, 4. And then I have a negative slope. So my function g of x, let's actually draw that in a different color. We'll draw that in blue. It's got to look something like this. So here this is g of x, and then this is, f of x. And we're looking for the region between negative 2 and positive 1. So I'm looking for, I would assume, this region right here. What is the area of this region? The one thing I am unsure of, and the one thing that makes me nervous, is this point of intersection. If they intersect somewhere in between this interval, if they intersect somewhere between negative 2 and positive 1, in that case, we would need to split this up into two separate integrals, because in that case, what the area would look like, I'm going to draw a different picture. In this case, my area bound between those two functions, I would have some of my area right here, but then I would also have some of my area right here, in which case my upper and my lower function flip. So I need to make sure that the intersection is either at 1 or outside of 1. So I'm just going to verify where f of x and g of x intersect. And the way I'm going to do that, I'm just going to take these two functions, set them equal to each other, and solve that equation. So I'm going to take 2x squared equals 4 minus 2x. This is a quadratic equation. The easiest way to solve a quadratic equation is to set it equal to 0. So 2x squared plus 2x minus 4 is equal to 0. Let's see here, I can factor out 2. That'll leave me with x squared plus x minus 2 is equal to 0. And let's see, this will leave me with 2 times x. Let's see, x plus 2 times x minus 1 equals 0, which will give me x equals negative 2 and x equals positive 1. And this is a huge relief for me. And actually, this tells me I'm going actually all the way to the left to that other point of intersection. That means that the points of intersection actually happen. This happens at x equals 2, and this occurs at x equals 1. And this is nice because it gives me this nice self-contained area. I have actually, those two are the endpoints of my interval. If I had, say, x equals 1/2, or x equals 0, or x equals negative 1, some number that's between negative 2 and positive 1, then I would have some more work to do. But because they are the endpoints themselves, I'm not going to have any problems. So I'm going to set up my integral first. I want the definite integral from negative 2 to positive 1. And now I need to determine what is my upper function and what is my lower function. So look at this yellow shaded region that I've created right here. If you need to, draw a vertical line in there. Where does the top part of that vertical line hit? Well, that top part of the vertical line is hitting the blue function, g of x. So that means that g of x, that's actually my upper function. So this is my upper curve. And then down here, the parabola at this point right here, this is my lower curve on that region. So my upper curve is g of x. I'm going to have 4 minus 2x minus my lower curve, which is f of x. That is 2x squared dx. So this is the definite integral that I'm trying to evaluate from here on out. So let's see if we can do that. Here it doesn't really simplify to all that nicely. I will have, let's see, -2 to +1. I've got 4 minus 2x minus 2x squared dx. There's no like terms or anything that I can combine. So first thing I need to do, of course, is find my antiderivative. So I should have 4x minus x squared minus 2x to the third over 3. And I'd like to evaluate that at 1 and -2. So let's see, I have 4 times 1 minus 1 squared minus 2 times 1 to the third over 3 minus 4 times -2 minus -2 squared minus 2 times -2 to the third all over 3. So let's see if we can take our time here with this. I will have, and actually let's just do it right below, 4 minus 1 minus, this will be 2 over 3 minus, over here 4 times -2, I've got -8. -2 squared, that'll give me minus a +4. Minus here 2, let's see, -2 to the third would be -8 times this. I'll actually have plus 16 over 3, excuse me. This would be -8 over 3 times -2. Yes, 16 over 3. So let's see. I'm going to simplify this a little bit at a time here. 4 minus 1, this is 3 minus 2/3. Minus over here, this is -12 plus 16 over 3. I'm just going to go ahead and distribute that minus sign through right now. So let's see, 3 plus 12, I've got 15, and -2/3 minus 16/3, I've got minus 18 over 3. So I have 15 minus 6, which gives me 9. So the area bound between those two functions is 9. So a lot of work, I think, went into setting this up. We had to make sure that we didn't have a point of intersection within our interval. That was the first thing that we did. Actually, excuse me, that was the second thing we did. The first thing that we did was actually graph the two functions together. So we graphed the two functions. We verified that the points of intersection were either on the endpoints like they are here, or if they're outside of that interval. If they're outside of -2 to +1, then we don't have anything to worry about. We set up our definite integral. We said here's our upper curve, that is g of x, that's the blue function, minus my lower function, 2x squared, which is the black function, the parabola. And then we just evaluated this definite integral. So there are a lot of steps to these, but once you get this problem set up, once we got to, say, this step right here, this should feel really, really familiar to the types of problems that we were doing in the last section. We should end up with just a definite integral that we should evaluate, and we know how to do that from the last section. So really the new ideas in this section are just setting up this definite integral, which will tell us the area between the two curves.